last video I had you just focusing on the Millikan oil drop experiment and the discovery of the electron, and we saw that it really was an issue of force balancing. And especially on that Millikan oil drop experiment, you're trying to balance the force of gravity with the electrical field force. And by doing so, Millikan was able to decide what he thought the mass of an electron was. Okay, now I'm going to do a problem. It's a little bit simpler than Millikan's, of course. But we have, let's say, an E field. So an E field could be produced by having two charged objects, maybe something positively charged and something negatively charged. And then what's going to happen is the field lines coming out of the positives, well, I'll draw these lines first and then I'll say something. I'm going to say it a little differently. You don't have to draw like a one-to-one sort of thing, but imagine a bunch of field lines going from the bottom plate to the upper plate. Okay, so burying yourself down in this problem, what's really going on is you have a lot of little upwards and a lot of sideways fields. So any charged particle down on the bottom plate, right, is really exerting E field in every direction. But so is its neighbor, right? So is its neighbor. So let's say you have this black guy and you have this red guy, and then these two are positively charged. So you can see that all of these vectors that have any kind of horizontal component are going to be destructive. So I'll highlight a couple in green when I'm talking about our, like this vector and this vector, right? The y's build, but the x's cancel. Or perhaps this vector and this vector. The y's build, but the x's cancel. Same with this vector and this vector. The y's build, the x's cancel. But the x's cancel everywhere. You might say, what about these ones over here? Like these ones don't have a cancel. Yes, they do. There's another charge. Let's make him blue. He's over here, see? And any field lines that are coming out of the red, going slightly to the right, get canceled by field lines that are going out of the blue, pointing slightly to the left. So now, see, these have y's that construct, but x's that destroy, see? And these, and these. So basically, nothing horizontal survives at all. But all the vertical components construct. And this forms an upwards field from the bottom plate straight up. Now, meanwhile, up at the top are some negative charges, and they're up there, and all their field lines are pointing in towards themselves, right? So up here at the top, you might have a similar situation. You've got the little black charge, and he's negative, so all his field lines are pointing radially inward. And then you got the red one, and all of his field lines are pointing radially inward. These are not the field lines caused from the bottom plate. These are the field lines caused from the top plate. And then maybe there's a blue one over here. I wish I had more than 3 colors. Okay, so as you can see, the same thing is happening. The horizontal components come in pairs. So this vector and this vector, one's pointing sort of up into the left, one's pointing up into the right. Those kind of destroy each other, but not the upward parts. So you actually get 2 upwards from that, see? And then, obviously the one that's directly to the left and the one that's directly to the right, those completely cancel, there's nothing left over. But let's look at a pair up top. So you've got this pointing here and this pointing here. I'll highlight those in yellow. It's getting kind of cluttered. So I'm looking at these 2 yellow ones up here. One's pointing left and down, the other's pointing right and down, but the left-right thing cancels out, leaving you with just down-down. Okay? Now, since we're not really on the back side of the plate, we're in the front side of the plate, we don't really experience anything I just highlighted in yellow. So in other words, we don't really have to think too much about this top half of this. And down below here with our 3 charges that we drew earlier, we don't have to consider anything happening down in this yellow region either. Okay, because we're only experiencing between the plates, not what's behind the plates. So, all right, this is kind of an ugly drawing, but imagine 2 plates that have net charge on them. I think the E field would look something like this, straight up, all the way. Now, what happens when you send an uncharged particle through? It just goes straight through. Why? Well, it might fall a little due to gravity, you know what I mean? So it might fall a little due to gravity, actually. But technically, if this was a top view looking down, and you're looking from above the Earth toward the center of the Earth, gravity might be pointing into the page. So if the force of gravity is pointing into the page, then you would not see any vertical deflection here. It just kind of pass right through. It's because there's no charge on it, and it doesn't experience electric forces. Just like non-massive objects have no effect from gravity, like gravity doesn't affect them, in the same way, non-charged objects just don't feel electric fields. They just don't experience it. Okay, let's go ahead and put gravity pointing this way. Force of gravity. Do I even want to consider gravity on this problem? Let me think. I might change my mind, not even do the gravity thing. Might be a little complex. Yeah, I think I'll stay away from gravity. I think what I'll do is I'll make gravity point into the page. So this is like a desktop apparatus, and the two plates are like kind of like ping pong nets on the desk, and the E field is pointing, straight across the desk like this, and then the charged particle is going to go wee right through. Okay, so it does experience gravity, but not in the direction of the field. All right, so now we send a charged particle through. Let's draw that black, I guess, and let's just, for the sake of argument, say that he is a positive charge. So he comes in to the field and he says, "Whoa, field." Okay, he's very attracted to the top plate, but not so much to the bottom plate. Now, the other thing I didn't tell you is he's going really, really fast. So not near the speed of light or anything like that, but he's going pretty fast. And so this is a short distance. He's kind of flying into this forest of E fields, and he is deflected by this. Once he kind of escapes the influence of the field, more or less, he'll continue traveling in a straight line. But he came in a straight line. He got deflected, and he's flying off in a different direction. Okay, so that was because of the attractive force experienced during this time interval. Okay, now this distance, let's just call that L. We'll say that the charge is Q, and let's get busy checking to see what the vertical deflection would be for this particle. So he's going to be going, from this Y value to eventually up to this Y value. So we call that a deflection, right? So from Y initial to Y final. And if you guys don't mind, I'm just gonna call that Y. Well, in the end, I'll just call it Y. Okay. So the first part of this is really just a free body diagram. The particle is experiencing really one force, right? And that force is the force due to electrical field. So force of electrical field is always charged particle that's experiencing the field times field value, right? So it's F equals QE. That was what the last video was all about. All right, so that's not too bad. But wait a minute. The force is only vertical, right? The force is only vertical. So although the particle's moving sideways at every instant, when it is moving along, right, through the field, at every instant, it's only experiencing an upward force. Well, in the page, it's upward, okay? So it's experiencing an upward force, and it's a constant force. Why? Because the force only depends on the charge amount and the field amount. The field all through this region is uniform. Notice that these red lines do not get closer to each other. They do not diverge apart. Just nice straight lines equally spaced all the way across. That means that the field is uniform throughout. Okay? Now, of course, that implies that the original charges were laid out uniformly. So we are assuming uniformly charged plates. Okay? So maybe they are conductors, and the charges have already distributed themselves into an even and uniform way. Or maybe it's an insulator, and it's purposely designed to have a uniform charge. Okay, but because the field is uniform throughout the space L, and because the charge never changes, the force never changes. And constant forces are very easy to work with. We can use the kinematics equations for that. Okay? So we're going to write MA, Y. MAY just means mass times acceleration, and we only need a y component for this, equals Q EY. Now, EY is redundant. EY is redundant. E was already pointing in the y direction. So all of E is pointing in the y. We don't have an EX, so we'll just put E, if you don't mind. All right, so we end up with getting, this little equation. And what can we do with it? Well, we also learned, and this should have been part of your experience, but if you haven't had physics, that's okay. We know that the change in position of a particle, x minus x naught, I'm going to use y because we're talking vertically, y minus y naught should be the integral of the y component of the velocity dt. So position is always the antiderivative, change in position is the antiderivative of velocity. And this is from t initial to t final, right? Okay. And Mr. Shore taught this in BC Calc. I know not all of you took it. So we have basically y sub final minus y sub initial should be the integral of the velocity in the y direction, right? You could also say the same for the x's. So x sub final minus x sub initial equals integral from t initial to t final v sub x dt, right? Okay? So I'm just writing down facts right now, things that are kinematically important that not everyone has thought about yet. Okay? So it's dynamics when you're saying, hey, look, the force is equal to QE or the force is equal to MA. That's all dynamic stuff, meaning forces and things. Kinematics is more talking about the actual, speed versus distance and acceleration versus, speed versus velocity. Displacement versus velocity and speed versus distance and the like of those. So like acceleration versus velocity and acceleration versus displacement, all those ideas. Okay, so I'm just writing down some little formulas. Another one that you've probably seen before is that y final is y initial minus v initial in the y direction times t, or technically plus, and then plus 1/2 times acceleration in the y times t squared. But see, this is what you get when you integrate. So you can think of it this way, or you can think of it the way I wrote it over here. Okay. So anyway, this is kind of a relationship between y's. You can do the same for x. So like x sub final is x initials plus v sub xt plus 1/2 a sub xt squared. But these two equations on the left come from the integrations on the right. Okay. So what if you need, I know this is kind of a review, what if you need Vy and you don't have it? Well, Vy comes from integrating acceleration. So like you could write, Vy final minus Vy initial is the integral of acceleration y dt from t initial to t final. That's supposed to say t sub f. Okay? So what I'm saying is you can get your velocity function here, and then you can plug that into here and integrate again to get your change in position. And so we can do this all with calculus. I'm actually a little on time today. I'm going to go ahead and just use the y equals y naught plus v sub yt plus a sub y t squared. So it's y. And since we only care about the deflection, we really want y sub final minus y initial. So I'll just put change in y equals v sub yt plus 1/2 a sub yt squared, right? So what is v sub y? Well, initially it's 0. When it comes in, and this is supposed to, I just labeled it, it's actually v sub y naught, or v sub naught y. It's the initial velocity in the y direction. Well, when the particle came in, it didn't have any velocity in the y direction. So I'm obviously treating left and right as x and up and down as y. So this is actually just 0. And this tells us that delta y, which is what we're looking for, is 1/2 a sub y t squared, right? But if you look up here, you'll see where I put the stars that a sub y can also be thought of as QE over m, right? QE over m. So that's a dynamic idea from the dynamics earlier, but we can certainly use it. So let's plug that in. and we get delta y is equal to 1/2, and then we have QE over m times t squared. One last thing to do. How long does it take for the particle to pass through the field? In other words, how long does it spend in the influence of the field? Because if you let t be 1 second or whatever, then that might just only give you a partial deflection. Like maybe the particle spends 5 seconds in the field, plugging in like 3 seconds or whatever is only going to give you this deflection. Maybe 4 seconds will give you that deflection. Maybe you need to put in all 5 seconds to get to this deflection. So since we don't really know how big L is and how long this table arrangement is, and we don't really know how fast the object was moving when we started, we'll just assume it came in with a speed v. So enters with speed v. And it traveled a total distance of L, right? It traveled a total distance of L. So we know that distance is basically rate times time when something's not speeding up like that. So keep in mind, the vertical speeds are changing on the charged particle as it is in the field. At first it had no vertical speed, and then it started to pick up a little vertical speed, picked up a little more vertical speed, picked up a little more vertical speed, but it never picked up any speed in the horizontal. Whatever it came in with, v sub x or whatever, is what it left with. So I'll call it v sub x, but it is constant throughout that time. So for that, you can just use distance as rate times time. Or in other words, L is v sub x times t. So this tells us that t is L over v sub x, and that's what I'm going to stick in last. Okay? So I know it's messy, but I'm going to go down to the very bottom, erase a couple things that are already there and I don't need anymore, and I'm going to write my answer in green pen. So delta y is officially 1 over 2 QE over m, and then I'm sticking in an L over Vx, and it's squared. So my final answer is this, QEL squared, lowercase l, all over mvx squared. This is our deflection. Now why is this important? Well, you might actually have a table experiment like this someday, and you want to know, or you'll send a charged particle in with a certain speed and mass, and all of a sudden you realize, hey, it deflected a centimeter. Well, you happen to know delta y. You happen to know m and v. You happen to know the E field because you built this thing. You know L. You could find the charge on that particle. This is not too different from really what Millikan did. Obviously his is way more sophisticated, but this would be a great way to find the charge on a particle whose mass velocity, sending it through an E field of length